Can someone respond?
Good morning, sir.
Yeah. Can you see my book?
Yes, sir.
Everybody can see my book?
Yes, sir.
Good morning, everyone. Good morning, everyone. In the last class, we have come across synchronous counters. There are two more counters to be discussed from this chapter, in which the first one is called as ring counter. The first one is called as ring counter. What do you mean by ring counter? Okay. Can anyone respond? Is it visible? My book is visible and I am audible.
Yes, sir.
Okay. So today we will see.
Yes, sir.
Yeah. Thank you. We will see ring counter as one example. So what is a ring counter? Before we see ring counter, we would like to see something about timing signals. In a digital computer, if you take any computer, the operations of digital computer, the operations of digital computer are managed or synchronized by timing signals. So there is a concept of timing signal. So there is a timing device in every digital computer which keeps counting timing signals T0, T1, T2, T3, etc. So every digital computer requires a timing device which counting timing signals. According to the timing signals, varieties of operations will be performed. రండి పర్లేదు పంపలేదు మీరు పంపుదామని మీరు చెప్పండి అంతే పంపిస్తాను ఎంత పంపను okay T0, T1, T2, T3 and so on and so forth. The timing devices will calculate. For example, usually when in a digital computer during execution of a instruction, we call it as execution cycle of instructions. This is not like I'm for the sake of understanding timing signals, I have been telling this introductory part. During executing an excuse me, During executing an instruction, when timing signal ticks T naught, the computer performs various operations. So some data will be transferred from one register to another register. During the next timing signal, some other data will be transferred from memory to another register. So different, these are the operations. Computer performs operations against timing signals. So these timing signals are generated by timing devices. So these timing devices generates timing signals at a regular intervals. So how timing devices are designed within a computer system is by means of ring counter. So ring counter is such a timing device which generate timing signals. That is the specialty of ring counter. Let us see ring counter, how it is constructed and how it works. For example, ring counter consisting of 2 to the power of n flip-flops to generate 2 power n timing signals. This is logic. Means, for example, if you want to generate 4 timing signals, we need 4 flip-flops. This is the logic. To generate 2 to the power of n timing signals, a ring counter requires 2 to the power of n flip-flops. What I'm telling, just for example, let us assume we want to generate four timing signals, so which requires 4 flip-flops to be used. Which requires 4 flip-flops to be used. So I'm now explaining the design of a ring counter with 4 flip-flops to generate 4 timing signals. Got my point? See, the design of ring counter looks like this. My ring counter looks like this. See, 4 flip-flops. I will take 4 flip-flops. 1, 2, 3, 4. The name of the first flip-flop is called T naught. The name of the second flip-flop is called T1. The name of the next flip-flop is called T2, T3. There are 4 flip-flops: T naught, T1, T2, T3, and these are their outputs. Got it? The T3 is connected back to T naught. And there is a shift right control. There is a shift right control. For example, the initial value of T naught, T1, T2, T3. See, this is the register T naught, T1, T2, T3. I will take 1000 initially. I will take 1000 initially. See, now who is active? What is the timing signal is active? See, T naught is 1, T1, T2, T3 are zeros. Means T naught is active. For example, now we apply this shift right operation. What happens? This one goes here, this one 0 comes here, this 0 comes here, this 0 goes out. See, T3 is given back to T naught, so this 0 come and join here. Now you see at the this is during first cycle. This is during second cycle. See, during second cycle, who is active? T1 is active. Again, you apply shift right. During third clock cycle, what happens? This 0 comes here, this 1 comes here, this 0 comes here, this 0 goes out and come and join here. See, now who is active? T2 is active. Again, during the fourth shift right operation, it becomes 0, 0, 0, 1. That 0 goes out. So now who is active? T3 is active. So we started with 1000. With the help of shift right operations, first T0 is active, next T1 is active, next T2 is active, next T3 is active. Again, T0 will be active, again T1 will be active, again T2 will be active, again T3 will be active. So this will be in a continuous slope. So a ring counter, to generate 4 timing signals, we require 2 to the power of n flip-flops to generate 2 to the power of n timing signals. This is how a ring counter can be generated. So there is an alternate design for ring counter. Alternate design for the ring counter. It looks like this. In alternate design of ring counter, I will take a 2x4 decoder. A 2x4 decoder consisting of 4 outputs. See, 2x4 decoder, 2 inputs, 4 outputs. The outputs are called as T0, T1, T2, T3. See, these are the timing signals. These are nothing but timing signals. There are 4 timing signals being generated by 2x4 decoder. The 2x4 decoder shall receive 2 inputs. The 2 inputs are received from a counter. I have a counter with 2 flip-flops AB such that when A and B are 0, 0, T0 is active, 0, 1, T1 is active, 1, 0, T2 is active, 1, 1, T3 is active. So in this ring counter design, this above ring counter is generating 4 timing signals using, see, one 2x4 decoder and 2 flip-flops. See here, this ring counter generating 4 timing signals using 4 flip-flops. Here we have been using only 2 flip-flops. Here we are using 4 flip-flops. Of course, you need a 2x4 decoder. Here nothing is required. This is how ring counter can be designed and understood. Ring counter can be designed and understood. Now we will see the last topic from this unit, that is called as Jhonson counter. A Jhonson counter is also called as switch tail ring counter. Another name for Jhonson counter is switch tail ring counter is another name for Jhonson counter. So even Jhonson counter is also used to generate timing signals. Jhonson counter is also used to generate timing signals. Now let us see how Jhonson counter is designed. Since it is called a switch tail ring counter, the design looks like this. 1, 2, 3, 4. Okay. All 4 flip-flops are of type only D. The name of this flip-flop is A connected to this. The output of the second flip-flop is B connected to the input of the third flip-flop. This is called C connected to the third input. And this is called E because D already we are using. That's why I named it as E. The E is connected back to D. The E is connected back to D. Not E exactly. The complement of E is connected back to D. And every flip-flop is having common clock. See. First flip-flop is D, name A. Second flip-flop type D, name B. Third flip-flop type D, name C. Last flip-flop also type D, name D. The complement of E is connected back to D. See here, in the ring counter, T3 is connected to T0, but in the switch tail ring counter, the complement of T3 is connected. The complement of T3. Let us take an example, the initial value. Initially, I have taken 0, 0, 0, 0. Means a 0 here, 0 here, 0 here, 0 here. Okay. For example, if you shift, this is called sequence 1. In sequence 2, we shift the contents. What happens? This 0 comes here, this 0 comes here, this 0 comes here, this 0 goes out. And since I am complementing, 0 becomes 1, that 1 will come and join here. See, this is the second one. See the third sequence? Okay. This 1 comes here, this 0 comes here, this 0 comes here, this 0 goes out and complemented, come and join here. This is the third one. Fourth sequence. 1, 1, 0, 1. Fifth sequence. 1, 1, 1, 1. This is fifth sequence. Now you see sixth sequence. What happens to sixth sequence? This 1 comes here, this 1 comes here, this 1 comes here. This 1 goes out, complemented and join here. This is the sixth one. Seventh one, you see. Seventh one, you see 0 come here, this 1 come here, this 1 come here, this 1 goes out, complement and join here. Eighth, 0, 0, 1, this 1 come and join here. That's all. So with the 4 flip-flops, we can generate 8 different sequences. 4 zeros, 1 triple 0, double 1 double 0, triple 1 0, double 1 double 1, 0 triple 1, 0 double 0 double 1 double. This is only possible because we have connected the complement of the last flip-flop, the first flip-flop. So we can generate different timings. Let us call them as T0, T1, T2, T3, T4, T5, T6, T7. Means we can generate 8 timing signals with only 4 flip-flops. That is the advantage of Jhonson counter. In ring counter, we can generate 4 timing signals with 4 flip-flops. In alternate design for ring counter, 4 timing signals can be generated using 2 flip-flops and 1 2x4 decoder. In Jhonson counter, 8 timing signals can be generated using only 4 flip-flops. This is the end of 4th unit. So by this 4th unit is over. Now let us move to the most important unit and very easy to score marks in examination. That is called unit 5. The name of the unit is memory and programmable logic. The name of this unit is memory and programmable logic. Okay. Now let us first focus on memory. Then we can go to programmable logic. What do you mean by memory? Every digital computer have storage, because without storage, that is called memory, a computer serves no purpose. This we understand already. So digital computers have storage. That storage we call it as a memory. Okay. So what is the type of memory is available in digital computer? Can be understand by memory hierarchy diagram. By a diagram called as memory hierarchy. What do you mean by memory hierarchy diagram? At the bottom of the diagram, we will be having auxiliary memory devices. On its top, we will be having secondary memory devices. On its top, we will have primary memory. On top of primary memory, we have cache memory. On top of cache memory, we will be having registers. See, auxiliary memory, secondary memory, primary memory, cache memory, registers. So there is a variety of maintenance of these registers. Every digital computer shall have all types of memories. Why all types of? Why can't we make the digital computer storage made up of only auxiliary memory, or only registers, or only primary memory? Because there are a lot of issues here. For example, if you look at the size from top to bottom, the size increases. Means registers are the smallest devices. Auxiliary memory are the largest device. In the same way, if you look into speed, from top to bottom, speed decreases. Means registers are the fastest memory devices. Auxiliary memory is the slowest memory devices. Got my point? So size from top to bottom increases. Speed from top to bottom decreases. In the same way, cost. Cost also, from top to bottom, cost also decreases. Means registers are the most costly. Auxiliary memory is the cheapest memory. Got my point? See, how do you understand? Registers are small in size, but fast, but expensive. Auxiliary memory is large in size, but slow and cheap. If whole computer's memory is made up of auxiliary memory, we will have large memory, but very slow, but very cheap. So your purpose will not be solved. Computer becomes very slow. For example, if the whole computer storage is made up of registers, what happens? Computer becomes very fast, but too costly, becomes very small. So now what is the question? We have to make an equal mixture of all these types of memories. Here, the most important memory is called primary memory. The primary memory is nothing but random access memory, RAM and ROM, read-only memory. Secondary memory means hard disks. Register, you know already, there is some special memory in computer called as cache memory. Primary memory means RAM, ROM. Secondary memory means hard disk. Auxiliary memory means pen drives, CD drives, flash drives, etc. will come into auxiliary memory. Okay. Now here in this unit 5, we have to study the primary memory. Primary memory is our criteria. Okay. Let us first study primary memory. What do you mean by primary memory? Just now I have explained you primary memory of two types. One is called RAM, also called as random access memory. The second one is called ROM, that is called as read only memory. Let us first have a look at RAM. So RAM stands for random access memory. RAM stands for random access memory. We can perform two operations on RAM. One is called writing, the second one is called reading. Means the content of a random access memory, for example, if you write like this 0 and last the memory is 1023, means there are 1024 words of memory. For For example, each of size 1, 2, 3, 4, I'll say 1024 words by 4 bits. Means there are first word, second word, 5, 6, 7, and so on. The last word is 1023, means there are 1024 words, and the size of each word is 4 bits. So the size of random access memory can be written as number of words by number of bits. We can perform two operations. One is called writing, another one is called reading. Means write means we can send data to RAM. Reading means we can read data from the RAM. So two operations we can perform. To understand it in a better way, let us try to understand with the help of block diagram of random access memory. This question only will come into examinations most of the times. Okay, how does block diagram of RAM looks like? The block diagram of RAM can be explained by this. For example, I am having a random access memory RAM. See, the size of the memory is 2 to the power of k words by n bits each. Means there are 2 to the power of k words, and the size of each word is n bits. There are 1024 words, and the size of each word is 4 bits. This is an example. Here 2 to the power of k words with the size of each word is n bits. This is called random access memory. See, each word is n bits. Since there are 2 to the power of k words, I need k bit. This is called address line. ADDR, address. Address is k bits because 2 power k words are there. I'll explain you why k bits. And there are two special control lines. One is called read line. The next one is called write line. Means if read is active, read operation will be performed. If write is active, write operation will be performed. N input lines. To send data inside, we need input lines. How many input lines required? N. Because what is the size of the each word n bit kadapatti? N input lines. And if you want to read data from the RAM, we need n output lines. Input lines and n output lines are n because the each size of each word is n. The number of address bits are k because number of words are k. Let us take an example. I have an 8 by 4 RAM. The size of my RAM is 8 by 4. What do you mean by 8 by 4? I will be having 8 words. And the size of each word is 4 bits. Imagine. See, 1, 2, 3, 4. Each word is 4 bits. I have 8 words. I will call this as 0, 1, 2, 3, 4, 5, 6, and 7. See, I have 0 to 7 words. Means how many words? 8 words. What is the size of each word? 4 bits. 8 by 4. Let me write the contents just for sample. What is the value stored at address 0, 0, 0? See, this is called address. 0, 1, 0, 1. Something 1, 1, 1, 1, 1, 0, 1, 0. 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. Something. So this is called address. How many words? 8 words. If I write binary address, 0 means 0, 0, 0. 1 means 0, 0, 1. 2 means 0, 1, 0. 3 means 0, 1, 1. 4 means 1, 0, 0. 5 means 1, 0, 1. 6 means 1, 1, 0. 7 means 1, 1, 1. So total how many words? 8 words. 8 is less than or equal to 2 power n. What is n? 3. Amma, please mute yourself, somebody. Aparna, can you please mute yourself? See, random access memory, if there are number of words 2 power k, address is k bits. In this example, how many words? 8 words. 8 is less than or equal to 2 power k. The k anta 3. That's why see, address is 0, 1, 2, 3, 4, and so on. So this is the content. This is how we will understand the block diagram of RAM. How do we read? See, if we activate read input, see how do we perform read operation? For example, I want to access the content of second word. How do we read? Read input active cheyandi. The address 2 ni k bit address kin ivvandi and supply the address at address line. Active the read content. Then on the output lines, this value 1111 will be visible here. How do we perform writing? Writing, for example, I want to change the content of fifth word from 0011 to 1100. Let us say. Very simple. What is the data to be written? Local game new data aim pump then output lines given. apply new data to output lines, give the address 5 at address lines, and activate write content. Then this data will be written at this address. So this is how we will perform read and write operations. This is story about random access memory. This is the story about random access memory. Just give me a minute. The random access memory is further divided into two types. One is called SRAM. The second one is called DRAM. SRAM means static random access memory. DRAM means dynamic random access memory. What is the difference between static RAM and dynamic RAM? Static RAM uses latches. Dynamic RAM uses capacitors. Only their making makes difference. Both of them are random access memory. Block diagram is simple. If there are two power k words, k address lines, read line, write, and everything is common, how do we make matters? Static RAM, the storage is given by latches or flip flops. Dynamic RAM, it is given by what do you say, capacitors. Okay. Now we have to understand how memory decoding is done in RAM. Memory decoding in random access memory. Okay. In random access memory, I have explained you. For example, take a 4 by 4 random access memory. What do you mean by 4 by 4 random access memory? Means I have 4 words. Word 1, word 2, word 2, word 3. And each word, see, 4 words. And each word will be containing 4 bits. See, this is called 4 words, 4 bits. Okay. For example, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1. Let us take an example. This is the design. Let us take an example. This is design. So each of these boxes, see 4 by 4 RAM means 4 words and each word containing 4 bits. So it leads to total 16 boxes. I will call each one of them as a box. If we want to say specifically, we call them as binary cells. Each one of them is a binary cell. Now we have to understand the design of binary cell. What is a binary cell? A binary cell is basic building block of random access memory. So we can understand binary cell in this form. Binary cell means each box shall contain, each binary cell will receive input and produce output and receive some special control like read or write, and reading jarutunda writing jarutunda cheppadam kosam, and also will have some special line called as select. See each binary cell, see I am exploding each binary. See each binary cell looks like this. Every binary cell shall have input received, can send output outside, will receive control what to perform, whether reading is performed or writing is performed. Select whether to select deactivate this cell or deactivate this cell. Means if the select is active, then only the cell will come into operation. If the select is not active, this whole cell becomes inactive. Means the whole operation becomes on selector. If select is 0, this cell becomes inactive. If select is 1, the cell becomes active. Once you understand this binary cell design, then we can understand memory decoding concept. The concept of memory decoding. The concept of memory decoding. For example, to understand in an easier way, I have been explaining memory decoding of random access memory using 4 by 4 RAM. I have been using memory decoding can be explained using a 4 by 4 random access memory. Understand? Means for example, 1, 2, 3, 4. See, first word, second word, this is second word, this is the third word, and I'm drawing the fourth word. See, there are 4 words. For this whole is word 1, word 2, word 3, word 4. Got it? So each one of them is a binary cell. The binary cell, it is a binary cell. It is a binary cell. Binary cell. BC, 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 BC. I am using a 2 by 4 decoder. I am using a 2 by 4 decoder with two address lines A0 and A1 because we know 4 by 4 RAM. If you take a 4 by 4 RAM, since number of words are 4, 4 is less than or equal to 2 square kabatti address ento ostadi 2 bits. C means 0 means 0 0, 1 means 0 1, 1 2 means 1 0, 3 means 1 1. What is the size of the address? 2. Because 4 words. 4 words means 2 square words means address is equal to 2 bits. See? Here also 4 words means address is 2 bits. This is a 2 by 4 decoder. Word 0, word 1, word 2, word 3. Because we know if you make A0 A1 as 0 0, word 0 is active. 0 1, word 1 will be active. 1 0, word 2 will be active. 1 1, word 3. Because this is a decoder. What is this? Since I have been using a decoder. Okay. See, these are all called as input lines. In the same way, we will have output lines. Every binary cell we gives you output and చెప్పాను కదా ముందు కాన్సెప్ట్ లో. These are called output. So inputs, outputs, select. If this is 0 0, 0th line will be active. 0 1, first line will be active. 1 0, second line will be active. 1 1, third line will be active. So depending upon the given address, a specific word will be selected. That is what we have to understand. This is called memory decoding. Same way, we have to understand another technique called as coincident decoding. Coincident decoding is used in static RAM. SRAM antaradandi. Coincident decoding is popularly used in SRAM. When the size of the RAM is large, means we have a large memory, how do we perform? Because you see here, if the number of words are only 4, we need to use a 2 by 4 decoder. For example, imagine we have a random access memory of 1024 by 8. Imagine a situation. If we have a random access memory of 1024 by 8, means we must have a decoder to implement this. We must need a decoder with 1024 outputs with 10 inputs, 10 by 1024 decoder. So to simplify this, when the size of the RAM is large, how do we understand this is? This process is called coincident decoding. This is a 5 by 32 decoder. This is another 5 by 32 decoder. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Means I am using 1024 by, for example, 8 random access memory I am using. The size of my random access memory is 1024 by word. 8. 1024 words is equal to 1024 is equal to 2 to the power of 10. Means my address is equal to 10 bits. The 10-bit address is divided into 5 bits and 5 bits. This becomes a row address. This becomes a column address. See, this is called column address and this is called row address. So 32 kabatti 1, 2, 3, 4, 5, so on and so forth. 32 vastayi. 32 columns kabatti 1, 2, 3, 4, 5, 6, 7, 8. So each box, each dot stands for a memory word. Understand? So 1024, when the size of the random access memory is large, let us say 1024, instead of having the random access memory starts from 0, and 1023 means one single column. The idea is to have 32 rows by 32 columns. This is one column by 1024 rows. This is 32 rows by 32 columns. Which is easy? This is easy. This concept is called coincident decoding. Arranging the memory words in row column format like a matrix. That concept we call it as coincident decoding. In the same way, there is another concept called as address multiplexing. Address multiplexing is used in dynamic RAM DRAM. Address multiplexing is used in another concept called as in another random access memory called as DRAM. In DRAM, for example, I have a dynamic random access memory of 256 by 256. Means there are 256 rows and 256 columns. Understand? So to design a 256, we need a 8 by 256 decoder. For columns also we need another 8 by 256 decoder. This 8-bit number is stored in an 8-bit column register. This 8 by 256, this 8-bit data is stored in 8-bit row register. The 8-bit row register is given to 8 by 256 decoder. 8 by 256 decoder have 256 rows. This 8 by 256 decoder have 256 lines. This 8-bit data is given by 8-bit. See, 8 by this is a 256 by 256 memory array. It means 256 rows and 256 columns. 256 rows decode cheyడానికి 8 bits kavali. The 8-bit address is stored in 8-bit row register. Here also 256 columns are there. Means which require 8-bit address. 8-bit address is stored in 8-bit column register. Now that's all, nothing else. So in dynamic RAM, we call it as address multiplexing. In static RAM, with same concept, we call it as memory decoding. Memory decoding and address multiplexing, coincident decoding. Coincident decoding in SRAM, address multiplexing in dynamic RAM. It is to manage the memory as a matrix. If you manage memory as a matrix, we call it as address multiplexing and coincident decoding. In matrix management of memory, we will have our memory words managed into rows and columns. This is called random access memory. The next topic is read only memory. We can perform only reading. Let us see the block diagram of ROM. For example, my random read only memory is the size is 2 to the power of k by n. If the size of the memory is 2 power k words by n bits, we know if the number of words are k, then the size of the address is k bits. Because the only operation is performed is reading, we will not have any control lines. Read cheyala, write cheyala, confusion ledu. N bit output. Because since we cannot write, input lines are not required. We need only output lines. For example, this is called read only memory. Means we can inquire what is the value inside. For example, if you want to know what is there at a fourth word, you give the fourth number at address line and look at output line, the content will be visible here. The only operation performed is only reading. Since no writing, no read-write control lines. Since there is no writing, no input lines, only writing or reading on the output lines. This is called block diagram of read-only memory. But ROM is very important in computers memory. How do we understand an internal logic of ROM? Internal logic of ROM chuddam. For example, take a 32 by 8 ROM. A read-only memory of 32 words, and the size of each word is, let us take an example, Let us take an example. 32 words and the size of each word is 8 bits. Let us take an example. So the internal logic of ROM looks like this. See, since 32 words, I need a decoder of 32. 0, 1, 2, 3, and so on and so forth. I need a decoder with 32 outputs. If there are 32 outputs, how many input lines? 5. See, 32 words are there. 32 is equal to 2 to the power of 5. Means the size of the address is how many bits? 5 bits. 1, 2, 3, 4, 5. I will call it as I0, I1, I2, I3, I4. So, since the size of the address is 5 bits, I'll take a decoder with 5 inputs. Since 5 inputs, there will be 32 outputs. Understand? So these are, so each line is called a word. Each line is called a word. Understand? What is the size of each word? 8 bits. So there will be 8 perpendiculars. 1, 2, 3, 4, 5, 6, 7, 8. There will be an OR gate at the end. This we call it as a programmable OR gate. So this is how 32 by 8 internal logic of ROM looks like. So each intersection is a binary cell, which can be either 0 or 1. So these each intersections can be programmed to make their value either 0 or 1. That's why the RAM is also called as programmable read-only memory, very popularly called as programmable read-only memory, called as PROM. PROM. PROM means programmable read-only memory. For example, how do we understand the internal logic of PROM? I will explain you with the help of an example. For example, I have a programmable read-only memory of size 4 by 4. I have a programmable read-only memory of size 4 by 4. I will draw the contents. See, means I have 4 rows, 4 words, 0th word, first word, second word, third word. And each word consisting of 4 bits. See, 4 words, 4 bits. For example, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1. See, this is my prompt with 1, 2, 3, 4 words and each word containing 4 bits. So how do we draw the internal logic of this prompt? The prompt internal logic draw cheyalantukondi. Prompt programmable read-only memory. See how many words? 4 words. So take a 2 by 4 decoder. See how many words? 4 words. Number of words is equal to 4 means 2 square means address is how much? 2 bits. Since address is 2 bits, I want to take a 2 by 4 decoder. 1, 2. This is called I0, I1. This is called address. See 2 by 4 got the 4 lines. 1, 2, 3, 4. This is called word 0, word 1, word 2, word 3. See there are 4 words. So each word is responsible for one sleeping line. And what is the size of each word? 4 bits. 1, 2, 3, 4. So I will be having 4 perpendicular lines. 1, 2, 3, 4. Give them to an OR gate. 1, 2, 3, 4. Now we have to see how do we construct. See, what is the value of the 0th word? 0th word value is 0, 1, 0, 1. Means this is 0, this is 1, this is 0, this is 1. This cross represents 1. Means where there is kept a cross means is called this line and this line. There are two. Let us assume 2 copper wires going one on the top of the other. If you blow them and take a soldering చేసాం అనుకోండి, these both lines will be attached to it. Means a cross means this junction is blown. Means it is logic 1. See logic 0, logic 1, logic 0, logic 1. What is the first word? 1, 0, 1, 1. 1, 0, 1, 1. Next 1, 1, 0, 0. 1, 1 0 0 0 0 1 1 0 0 1 1. This is how the programmable read-only memory logic is constructed. Is it clear? Is prompt clear?
Yes, sir.
So prompt, take the take the memory structure. Any words, number of words equal to number of sleeping lines. Number of bits is equal to number of vertical lines. Where there is a one, put a notch. Where there is a zero, leave the notch. That's all. Nothing else. Just give me a minute. I hope all of you understand the programmable read-only memory. See why this is called programmable? Because every coincidence means every junction may be programmed to become a 0 or 1. That's why we call it as a programmable read-only memory. Understand? Let us see one more example on programmable read-only memory, then we will see. Let us take an example. I have an 8 by 4 ROM. Means number of words are 8. Number of bits is 4. Since number of words is equal to 8, which is equal to 2 cube, means the size of the address is 3 bits. That's what we have to understand. We know 8 by 4 ROM means 8 words, 4 bits. Since number of words are 8, which is equal to 2 cube, the address becomes 3 bits. Okay. And the sample looks like this. Our ROM values are like this. See 8 words. And the size of each word is 4 bits. So this is my prompt. My programmable read on 0th word, first word, second word, third word, fourth word, fifth word, sixth word, seventh word. 0 0 1 1 1 1 0 0 1 1 1 1 0 0 0 0 0 1 0 1 1 0 1 0 1 1 0 0 0 0 1 1. Some example. Some typical programmable read-only memory of size 8 by 4. How do we draw the internal logic? The logic is very simple. How many words? 1, 2, 3, 4, 5, 6, 7, 8 words. So take one box with 1, 2, 3, 4, 5, 6, 7, 8. 8 words, 8 logics, 8 lines. 1, 2, 3, 4, 5, 6, 7. So this is a decoder. Of course, this diagram is a decoder. With how many outputs? 8 outputs. For a decoder, if the outputs are 8, how many input lines? 3. This 3 is called address. 1, 2, 3. Called as I0, I1, I2. Okay. 1, 2, 3, 4. Every word have how many bits? 4 bits. So 4 horizontal vertical lines. 1, 2, 3, 4. Connect them to a programmable OR gates. Single OR gate with which, because these junctions are programmable. See the content 0 0 1 1 0 0 1 1. Next double 1 double 0 1 1 1 1 0 0 0 0 0 1 0 1 1 0 1 0 1 1 0 0 0 0 1 1. That's all. The programmable read-only memory of size 8 by 4 is designed for this table. For this table, this is the internal logic of programmable read-only memory. This is the internal logic of programmable read-only memory. So now we can even use combinational logic implementation using prompt. Means we can use prompt diagrams to implement combinational logics. Combinational logic using prompt. For example, I am designing half adder using prompt. I am implementing half adder using prompt. For example, what is a half adder? We know. Take two variables x, y. There will be sum and carry. When 0 0, sum 0, carry 0. 0 1, sum 1, carry 0. 1 0, sum 1, carry 0. 1 1, sum 1, carry 1. Sorry, sum 0, carry 1. See, this is the table. So in this X, Y are called the inputs, sum and carry are called the outputs. So if we want to implement this using PROM, we have to treat inputs as addresses, outputs as contents. Inputs as address, outputs as contents. Means see how many rows? 1, 2, 3, 4. Means my programmable read-only memory consisting of 4 words. See, this is one word, second word, third word, fourth word. And how many outputs? 2 outputs. So this is called 4 by 2 PROM. So take a box with 4 lines called 0, 1, 2, 3. The names of the inputs as X, Y. This is a 2 by 4 decoder. How many inputs? Some carry only 2 standing lines. 1, 2. Give it to an OR gate. Give it to an OR gate. This is called sum. This is called carry. Write down 0, 1, 1, 0. 0, 1, 1, 0. This is called 0, 0, 0, 1. Sorry, 0, 0, 0, 1. That's all. Over. X, Y are the inputs. Since 4 rows, 4 horizontal lines, 2 outputs, 2 vertical lines with OR gate, programmable OR gate, with names of the outputs here, names of the inputs here. Connect the notches as it is. Is it clear? I mean, exam you will get one question on usual. There are 3 important questions from Unit 5. One is called RAM-ROM block diagrams. Second important question is Boolean function implementation using PROM. Then there is another concept called PAL and PLA. That's all. Unit 5 is over. Let us try full adder using PROM. What is full adder? We know full adder is a combinational circuit which takes 3 variables X, Y, Z and produces the sum and carry after addition. See how does the truth table looks like? X, Y, Z for sum, for carry. 3 variables covered 0, 1, 2, 3, 4, 5, 6, 7. See 0, 0, 0. What is sum 0? Carry 0. Carry sum 1, carry 0. Sum 1, carry 0. Sum 0, carry 1. 1, 0, 0, 1, 0, 1, 1, 1. Over. So as I told you, input stands for words. Output stands for contents. So take a box. How many? 1, 2, 3, 4, 5, 6, 7, 8 rows. So make up the 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. Call them as 0, 1, 2, 3, 4, 5, 6, 7. This is a 3 by 8 decoder. 1, 2, 3 inputs. One input is called X, second input is called Y, third input is called Z. And how many outputs? Sum and carry. So one vertical line for sum, another vertical line for carry. Put them to an OR gate. Put them to an OR gate. This is called sum. This is called carry. 0, 1, 1, 0, 0, 1, 1, 0. Again, 1, 0, 0, 1. Ikkada 0, 0, 1, 0, 0, 0, 1, 0, 1, 1. Over. What is this? This is nothing but full adder using PROM. Shall we verify? For example, when my X, Y, Z is, I want to verify this. When my X, Y, Z is 1, 0, 1, my sum must be 0, carry must be 1. Let us see. When X, Y, Z is 1, 0, 1, my sum must be 0, carry must be 1. Let us try. See, it's a 3 by 8 decoder. When X, Y, Z is 1, 0, 1, which line is active? Fifth line is active. What is the value of fifth line here? Nothing. Means sum is 0, cross, carry is 1. So this is how we can verify. So this is called Boolean function implementation using programmable read-only memory. Okay. We can solve many problems using this. One popular problem usually will come in examinations is, time does not permit. That is a pretty big problem. We will see in the next class. Is it okay?
Yes, sir.